Hi, my name is John Fortner, and this is my report for Lab 1, Constant Velocity. So this lab explores how a moving object under the influence of zero net force changes its position over time. And the main principle of physics that this lab is investigating is Newton's second law, which, especially the property that acceleration is directly proportional to the net force exerted on an object. So in this lab, our object has as close as possible to a zero net force acting upon it, and as a result, it moves with a constant velocity. So an important thing to grasp about this lab is that the velocity of the object we are under observation is constant because there is zero net force. So my analysis was based on the motion of a soccer ball rolling along a flat plane. So my reasoning for this was that I wanted to make the influence of friction on the ball or on the object as negligible as possible, and by using a rolling object, we can eliminate some of the impact of friction on the horizontal velocity of the ball. So this is my motion in tracker. As you can see, the ball rolls along the flat plane in a pretty much straight line. So I opted to have the ball move in the positive x direction because that seemed like the most intuitive thing for me. And I rotated my axes a little bit so that the ball would have a as one-dimensional as possible motion. So that it ended up being a rotation of 3.3 degrees above the horizontal. And since we're talking about the axes, this is a good time to bring up one of the questions posed in the instructions of the lab. If the axes had been flipped, there would be no change in the magnitude of the velocity of the ball. So that would remain the same. The only thing that would change is that in the velocity vector, the x component would be multiplied by a scalar -1 to reflect the change in direction. So this would be if it were going along the negative x axis. So a change in the axes would never change the magnitude of the velocity of the ball, even if it would change how the components were notated. So next, here's the data observed in the lab. So the column in the middle is the position as reflected or as was observed in tracker, and on the rightmost column is the position that was calculated in the GlowScript model. I used the same time step in GlowScript as passed between each frame and tracker in order to make the data easier to read. So as you can see, the data follows, it's pretty consistent between the two models. Here it is in a graph form. So as you can see, the tracker data goes a bit over the GlowScript model toward the middle of the experiment, but both ends are about the same, and the model is pretty consistent with the motion that we observed in the experiment. So finally, for the coding component, this is the program that I used. There weren't too many changes that had to be made from the starter code, but I added a graph of the velocity here, just to reinforce the idea that velocity is constant throughout the experiment. I updated the ball's mass, even though it didn't really come into play in this one. These are my initial conditions in these two lines. I had my time step as close as possible to 0.03 with the 3 repeating in order to reflect the same time step in tracker based on the frame rate of the camera. And finally, even though for the position update, a separate vector that never changed would have been sufficient, I wanted to use the ball's velocity just to make it so that the model would be more accurate even if the object did not have a constant velocity. So I also rewrote the velocity update formula a little bit based on Fnet and the ball's mass, even though it didn't really come into play in this experiment.